Mount Everest is Earth's tallest land mountain. The base of this mountain has an elevation of 4,200 meters, while the peak has an elevation of 8,850 meters above sea level. Okay, so here's this mountain. I'm just going to draw it looking like a ramp. And at the top of the mountain, the distance from sea level, okay, so our Earth is something like this, and the distance it is from the sea level is 4,200 meters. And at the base of the mountain now, at the top of the mountain, the peak is 8,850 meters. And at the base, it's 4,200 meters, okay, above sea level. So if we're thinking about our R value, R is the distance from the object to the center of the Earth. So we're going to have to add the radius of the Earth to the altitude to get the R value. Okay, so here's the radius of the Earth, here's the altitude, that 8,850 meters, and the total R value is when we add both of those up. Okay, so then that means that our initial, when we're at the top of the mountain, is the radius of the Earth, which is 6.37 times 10 to the 6, plus the altitude when you're at the top of that mountain, which is 8,850 meters. And when you're at the bottom or the base of that mountain, your R value is now the altitude, which is 4,200 meters, plus the radius of the Earth. Okay, so it's still 6.37 times 10 to the 6 plus the new altitude, 4,200 meters. Okay, so if I redraw this now, or if I just delete all of this messy bits over here, now that I know my R's, I'm all good. Okay, so this is my initial position. And this is my final position. And we're talking about a uniform solid disk. Okay, so it has a shape. It has a radius of 1.6 meters and a mass of 2.30 kilograms. It begins at rest, so our initial velocity is 0 meters per second. It's asking for angular velocity, so our initial angular velocity is also 0 meters per second. This disk is not moving at all, so it has a 0 meter per second or 0 radian per second. Angular velocity should be radians per second. Okay, it wants to know what the angular velocity is at the base of the mountain. So I'm looking for angular velocity final. That's what I'm looking for. Okay, so when it's at the top of the mountain, it has gravitational potential energy, and it has it begins at rest, so it has no kinetic energy. When it's at the base of the mountain at its final position, it has gravitational potential energy still, and it has kinetic energy. Okay, how do we know it has gravitational potential energy? Because we're not close to the surface of the Earth for the entire question, we need to use the long formula for UG. UG equals negative G m1 m2 over r. And with this formula, the reference position, or the value for r, that will give you a UG of 0 would be r is equal to infinity. So when we're infinitely far away from the center of the Earth, that's when our UG would be 0. We're not infinitely far away from the center of the Earth, so we do have a gravitational potential energy. Okay, so I'm going to say E total initial is equal to E total final. So initially, we have gravitational potential energy. We don't have kinetic energy because our V initial or our omega initial, they're 0. And at the end, we still have gravitational potential energy, but we also have kinetic energy. Okay, but this is a disk that is rolling, so it has translational as it goes down the ramp, but it also has a rotational as it rotates while it's going down the ramp. So I have translational plus EK rotational. So let me put in all the formulas now. So UG initial is negative G m. Now we're talking about the two masses here would be the mass of the disk and the mass of the Earth over r. initial, and we said our initial over here is equal to negative g mass of the disk, mass of the Earth, over our final, plus kinetic energy translational is 1/2 mass of the disk, it's the disk that's the one that's moving, times v final squared, plus kinetic energy rotational, so 1/2 I of the disk, omega final squared. Okay, so if the question was asking us for the final speed of the disk, then we would have to change the omega final to a v using the equation v equals omega r. But since the question's asking us for our angular velocity, we want to change this v final to be in terms of omega. So we're going to replace it with omega r. At the same time, we're going to replace this I of the disk. A uniform solid disk. If you look at the table with all the shapes and the moments of inertia, you'll see the moment of inertia of a solid disk is 1/2 mr squared. Okay, and again here we're talking about the disk, so it's the mass of the disk. And r, we're talking about the radius of the disk. Okay, so let's rewrite our formulas. So I have negative g mass of the disk, mass of the Earth, over our initial equals negative g mass of the disk, mass of the Earth, over our final, plus 1/2 mass of the disk. We want to get rid of that v final, so we're going to change it to omega r, and then when we square it, it becomes omega squared r squared. Okay, so this is our final omega, and this is our radius of our disk, plus 1/2 I of the disk is 1/2 mass times of the disk times radius of the disk squared times omega final squared. Okay, so now we have some simplifying to do. So 1/2 and 1/2 together makes 1/4. We have mass of the disk everywhere, so I can just cancel it all away. Okay, and then we have 1/2 omega squared r squared plus 1/4 omega squared r squared. So 1/2 plus 1/4 is 3/4. So let me rewrite all of this a little bit neater. So I have negative g mass of the Earth over r initial equals negative g mass of the Earth over r final, plus, so we said 1/2 omega squared r squared plus 1/4 omega squared r squared is 3/4 r squared omega squared. And we're solving for this omega squared. So I'm going to bring everything to the other side. I'm going to multiply everything by 4/3. And then I'm going to divide by r radius of the disk squared. And then I'm going to square root everything equals omega final. And now I'm going to plug in all the values. And yes, we should have a plus or minus here, but we're not looking for the direction that it's going. So I'm just going to take that out. So I have 4/3 times negative 6.67 times 10 to the negative 11 times the mass of the Earth, which you can find in your formula sheet. It's 5.97 times 10 to the 24. Divided by the radius of the initial radius, which is 6.37 times 10 to the 6, plus 8,850 meters. Okay, now I have plus g, which is 6.67 times 10 to the negative 11 times the mass of the Earth, divided by r final, so that's 6.37 times 10 to the 6 plus 4,200, divided by the radius of the disk, which is given in the question, it's 1.6 meters squared. And now my square root should cover the entire thing, so I'm just going to make it really big here. And now I'm going to type it all up on my calculator. So just note this 4 over 3 is times by everything that's in the numerator, so I should have put a big bracket here and here so it's more clear. And when I type all of this into my calculator, I get 154. This is omega final angular velocity, so the units are radians per second. So if I go back up to the question, I can see my units. I have 3 significant figures over here, 3, and here I have 3 significant figures. Here I only have 2 significant figures, so my answer should just have 2. So instead of writing 154 radians per second, I should really just be writing 150 radians per second. And notice here in this answer, this is not correct. So it should be 150 radians per second. All right, thanks for watching.